Today's speaker has a very special 25 years of software experience. He began his career at GE developing military flight control systems. Real brainy stuff. Please welcome today the Director of Systems Engineering for Actian, Laufenberg.
I think Mike, you guys hear me back there? Okay, great. So my name is Laufenberg. I'm the Director of Systems Engineering for Versant and Actian. I actually come to Actian through one of those acquisitions Paul described. I've been with Versant for roughly 10 years. Versant is an object database company, so that's going to be one of the databases we talk about. Actian, as Paul said, is a larger data management company, and we have products all over. I'm specifically going to focus on two of them. Okay. So, with apologies to Dickens, the title, A Tale of Two Databases, basically because A Tale of Two Cities is the classic compare and contrast kind of novel from the 1800s. It was published in 1859. I think we got close during the question and answers. I apologize too about the questions. I thought we were going to do the questions after the talk. They're going to be a lot easier. That doesn't really help you get the swag. In any case, it was best of times and worst of times is how Charles Dickens begins his classic novel. And really, that's kind of what we are or have today with data management. If you think about it, there are many, many choices out there. The whole NewSQL and NoSQL revolution in the last 4 or 5 years, maybe a little longer, has given us a tremendous range of choice in database systems. And that choice is kind of a double-edged sword, because with all that choice out there, you have to be able to understand the different components and how they work, and understand your system requirements. And as a systems engineer myself, my main job is to look at the problems that my customers are trying to solve and figure out which tools are the best fit for their particular needs. And that's what you really have to do, because any of these systems, they're going to be design trade-offs. What you want to do is going to vary depending upon what tool you pick is going to depend on what you're trying to do with your systems. So we have two databases, Versant and Vectorwise, and they have really different pitches within the data strip. So what are you trying to get rid of? In one case, we'll see that one of the things Versant does really well is gets rid of complex programming problems that might be very hard to do with SQL once you do them in the Java domain. Versus Vectorwise, which is really highly tuned for doing operational analytics and ad hoc queries. So there's a wide range of technologies out there today. We're going to talk about two of them, and they're kind of at opposite ends within the spectrum of database technologies. Versant is very much in the operational camp. Most of the Versant customers are using the system somehow in real-time systems where data is being updated continually. Vectorwise, on the other hand, is there to support ad hoc reporting, business intelligence type of applications. So in this 451 graph, you can see it in the upper right-hand corner of Vectorwise is there. So these problems, database problems, have been around pretty much since the beginning of computing. And many solutions have evolved over the years to address different kinds of problems. We're going to pick these two systems apart a little bit and understand why their choices were made. Again, another reason for picking a tale of two databases is if you think about the architecture of the system, they're a lot like cities. They have components and elements that they share. Two cities, in the case of Dickens' tale, takes place in revolutionary France, 1790s, written in 1859. These two cities get compared and contrasted. One's in the heart of the revolution. The other one is basically at one of its heights of military power. But looking at these two cities, architecturally, you see some common elements. They're both built on a river. They both have surrounding them large open areas for farms to support the city centers, palaces at the centers, higher density of population. So you see a common architecture, even though these cities are very, very different. We'll see the same thing with databases. When we look at the database architecture, there's a lot of common ground. You see file systems, logging, those kinds of things. The Versant architecture and the ParAccel or Vectorwise architecture. By the way, the new name is ParAccel SMP. I'm going to just call it Vectorwise because I think that rolls off the tongue much more easily. In any case, you see common architectural structures kind of in all database systems, but specifically these two, we're going to see how they share a lot of commonality and behavior, but yet differ in important areas that account for why their use cases are so different. There's one other theme that kind of comes up in the Dickens model, or Dickens story, that I actually think is kind of interesting when you think about data. Data really isn't stagnant anymore. It's created all over the place. It flows from one end to the other, just like water. In Dickens' tale, or the tale really to any city, we see these cities are built typically on the waterfront or on a body of water somewhere. And that's because there's economic advantage to that. The water makes life better in those cities. It's a resource that has great potential that can be extracted energy from, or it really becomes the life of the city. Well, data is the same way. If you think about how it gets used within a company. Lots of data there. It has to be stored, managed, taken care of. And it's also an economic resource that the companies are looking to exploit, be that through real-time analytic processing or operational side, where your database really is your business. So we're going to look at a couple of examples of each of these products just to give you an idea of where they're deployed. Now, it wouldn't be a story if we didn't have some antagonists. What problems are we trying to solve? And there's a bunch of things. You could probably come up with a list of another dozen issues that a database is going to have to address. A couple of my favorites coming from the object database side is development friction. How easy or difficult is it for the application designers to actually get information in and out of the database? How much work or friction is there between the Java programming model and the relational or the whatever the database model is? Complexity, volume, how much data is changing, what the queries are doing on. All these are challenges for database systems. What we're going to see is, depending on which challenges you have, different database approaches are going to solve those problems better. So these two databases fall into a broad category. One is very much model-driven. That is, the object-oriented database, that is Versant, is designed to deal with complex application models. We'll see examples shortly. Or dynamic types, where the data types change frequently. High update rates because of the fact that the systems used in real time running the business. One quick example might be airline reservation systems that a person is involved with. Anytime you book a flight, chances are you're hitting an operational Versant database. Vectorwise, on the other hand, you've got a broader class of information use. Instead of that highly engineered application that Versant is, with Vectorwise, your goal is really to connect with a lot of standard reporting applications, business intelligence applications. You have common tables that are used within the reporting structure across a wide range of reports and a wide range of applications. So you have more kind of a horizontal enterprise approach. So those two broad categories can kind of help define what you're trying to sell or solve, not sell. Although we'll sell too. So these two products, this is kind of my summary of what each of them does. One of them is high performance columnar database. The other one is operational persistence, native languages like C++ and Java. Interesting side note, I could have mentioned this in the questions and we brought it in. The person actually started off with Smalltalk, so if there are any Smalltalk programmers out there, we used to have a Smalltalk interface, but that's kind of fallen by the wayside too. In any case, there are things in the Vectorwise architecture that make it really good for this operational analytic kind of role. And there are things you'll see in the Versant architecture that really hone in on why it's a good operational database and solving very complex problems. So I think it's important to understand what a typical deployment for these systems might look like, give you a feel for what that looks like. So, ParAccel or Vectorwise typically sits in the middle of data warehousing kind of application. You might have your traditional online processing off on the left, some sort of ETL steps, data warehousing, storage. Where Vectorwise really comes in is on the business analytics and ad hoc kind of queries. So it's going to be used by your Cognos or other BI tools to give you very quick reporting off of your enterprise data. So it's in this kind of database in the middle role. It's there strictly for performance boosting because honestly you don't really want to run reporting on an operational database. You don't want to mess up the operations while you're generating this kind of reports. Yeah, there's a Hadoop interface for pulling data out of Hadoop and pulling it into Vectorwise. And actually, Hadoop is kind of fundamental to all of the Actian infrastructure. Really, if you look at the company as a whole, just kind of step out and talk for a second, we have elements pretty much everywhere in this domain, ETL, data flow management, not so much warehousing, although a little bit there too, and then the performance databases. Vectorwise is kind of a single node. We also have multi-node high-performance databases as well. Where we're really not is in the BI space, the reporting space. We're basically feeders for those kind of tools. So what's, to me, really interesting about Vectorwise is how efficient it really is. And when you look at this chart, it's basically one of the benchmarks. I encourage you to go take a look at TDC and to check out these benchmark results there. But there's two things to notice. You see about a factor of 2 performance over any of the nearest competitors. So that suggests we're doing something right within just the raw mechanics of answering the benchmark here. But the other thing to notice is the cost, the dollar efficiency. Vectorwise is really efficient, commodity hardware kind of thing. So when you take these two together, you see a pretty huge operational advantage with something like Vectorwise compared to these other databases. And again, take a look at tc.org. There's you get the full documentation of what the hardware is for these benchmark results. It's kind of an interesting read if you're into databases and performance. So that was Vectorwise typical deployment. I'd like to say there's a typical deployment for Versant, but there really isn't. Versant is really all over the map on the types of problems it's in. I briefly mentioned the airline reservation system. What is common with Versant is you have a very complicated domain model. You can see, you probably can't see, in fact, this UML here was meant to be more representative than something that you really want to look at. A lot of classes, a lot of interconnections between those classes, one-to-one, many-to-one relationships that are just fundamental within the application model. This is the kind of thing Versant deals with. I've got 25 classes or so represented on that little diagram. What's actually more typical is something that looks a little bit like this. This is actually a schema from one of Versant's customers. The schema itself is from the telecommunications space. It's something called the Shared Information and Data Model. It's a standard data model used to represent telecommunication management systems. Basically, the operational back-end for phone companies. Typical model there has over 3,000 classes, and those classes can have over 4,500 interconnections and relationships. It's a big, ugly, complicated model. And then when you start looking, again, this is just the schema represented here by the graph. When you start thinking about the objects that get instantiated on top of that schema that represent the flow of information in a telco system, you really start getting into complexity. That's the kind of thing that Versant is typically deployed in. Real complicated problems like that. So now we've got the stage set with the 2 different problem cases. Let's start looking at some of the architectural common grounds and differences between these 2 products. And if you've got experience with other databases, you'll probably recognize these same kind of components in pretty much any database system. These things have evolved over the last 30 to 40 years, and there's a lot of common elements. They all need some sort of data model. They all need communication systems or provide isolation and locking queries. Going to be somewhat important to a database, right? So there's a lot of these architectural components we're going to take a look at, trying to compare and contrast the Vectorwise and Versant. So that's actually the Versant architecture. And Vectorwise, Versant, it'll be in the slide deck if you want to look at it in detail. Well, let's start picking it apart. I figured it'd be best to start with a little bit of common ground right at the beginning. Anytime you're going to be capturing data, you've got to have some sort of data model. Vectorwise comes into this very naturally. If you're familiar with most relational databases, it uses, surprisingly, SQL. SQL's at the heart of everything with Vectorwise. It's kind of a drop-in replacement for just about any SQL database. Versant, on the other hand, not so much, but you see we still use the same integers and decimals and characters and strings and timestamps. So the data model, although its origins are a little bit different, coming from the languages of C++ and Java, the fundamental components that it used are really the same. So a lot of common ground there. Where we differ a little bit in the Versant model is being able to deal with the user-defined types. Pointers become very important in an object model. So we have to deal with the pointers or references, depending on which language you're using, and collection classes. Collections are a big deal in object-oriented programming. You have to have natural interfaces for those. So those are a little bit different in the data model. You don't see the same kind of things in the SQL side, although there are ways to mechanize it. In fact, object relational mapping tools do a fantastic job of kind of automating that mechanization of some of these OO features. For functional approach, SQL defines a lot of functions. You guys are probably all more familiar with them than I am, but just some broad categories there. One in particular, aggregation. That's something that Versant doesn't do particularly well in its queries, but Vectorwise is fantastic at it. The other thing we see here is where these things are executed. This differs quite a bit too. Being a SQL database, Vectorwise pretty much executes everything server-side. You put together a sequence of SQL commands, you ship them off to the server grinds on it, does whatever it needs to do, returns the information back to you. All that work is done server-side. The execution model in Versant is actually very different. It's more of a distributed model. Versant actually uses the application client, and the data is manipulated more by the client and not at all on the server. So we'll see that difference with one of the examples coming up here. So another key difference with that manipulation being on the client side is we really don't have, and this is one of the questions that will make a lot more sense now, we really don't have a mechanism for defining the schema like we do with SQL. SQL is the data definition and manipulation language, as well as the query language. With Versant, however, the C++ or Java actually becomes the data definition, or schema definition language. And that makes it very different. In the case of C++, we actually analyze the header files and extract the class model from that and define the schema. In the case of Java, we look at the bytecode, and we'll get into that in a little more detail. So manipulation languages are different. We do that on the Versant side through the programming language. So we have one really good for reporting, although we could theoretically use JPA adapter on Vectorwise. That's not typically how our customers use it, because it's not really in that kind of position within the system architecture, versus the complex interface that Java or C++ allows you to build. So just quickly, pictorially, same kind of thing. You see SQL at the top for Vectorwise. It's kind of the center of the universe. Standard network connectors to be able to let you get out data through either JVC adapters or OODB into Vectorwise. So that ought to be pretty familiar to anyone who's worked with just about any SQL database. The simplified view for Versant isn't quite as easy. If focus here is really the application, user application space. Versant supplies a set of libraries that you link into your application, and those make it really easy to access the objects in the database within your Java programming model. But it's a very, very different approach than the SQL concept. So quite often you have a development friction by having to use two different languages. If I'm writing a Java app and I need to get to the database, I have to do something to get there. And I might use an ORM adapter or JPA. I could use an object database. I could hand code NewSQL and run it through JDBC. Basically, the Versant architecture is set up to make that friction really minimal, make it easy for the Java programmer to get at the objects within the database. So let's talk about that just briefly, because it is so different from the SQL approach. So the whole goal with the object database is to capture the objects in memory, store those off into the database, and later on bring them back as fully hydrated objects, full collections of objects. In this case, Java example, this would be the JVM. I want to retrieve my objects, get them into the JVM, work on them, and get them back. The JPA and the code fragment, I hope you can see it in the back there, real simple. I decide what objects I care about. I mark it as persistent. Later on, I'm going to call commit. Between the two lines in red is pretty much standard Java code. I'm not having to jump into writing a bunch of SQL to do something to my database. I just manipulate the objects. We do that by starting with a plain old Java object, in this case, one employee class. And I have to add a couple of things to it. I add a tag that says that it's going to be part of a database. That's what the entity says. And then I give it an ID, because everything in the database needs an ID. And Versant will use a long ID, and that actually becomes the object identifier that is going to be at the heart of the Versant storage system. We'll get to that. But the enhancer then looks at your Java code that came after it's been compiled, and will actually add some information to that Java code. We call this enhancement. Basically, it looks at the bytecode, injects a bunch of new code into it to help with marshaling data back and forth between your application and the server. We add things like change or state tracking, so you don't have to worry about what's dirty, what's clean when the application calls commit. We add code to support what's called lazy loading, so only the objects that you actually use get marshaled into your application. And another concept of persistence by reachability. And that's simply, if I want to persist an object, I really am talking about not just that object state, but everything it's connected to. A lot of information is really contained in those connections and pointers. That's kind of what we're really realizing, and I think that's in part what's led to the popularity of some of the graph databases you've been hearing about. Really, Versant is in the category of graph databases. Our graph language is whatever is fundamental to C++ or Java. We can deal with all those kinds of relationships. So persistence by reachability, if I have a graph like this in my application memory and I just say make this red object persistent, later on when I call commit, everything that's connected to it is going to end up in the database because that is part of the state that needs to be captured. So the goal there is to make this as minimally intrusive on the programming language as possible, give you easy tools to add transactional semantics around the programming language, and also support the object-oriented concepts like inheritance and collections, that kind of thing.
Does it make copies of the developable copies?
No, actually, the copies typically get operated on in memory, and when you call commit, those objects get shipped back. So, good question. So, we've kind of taken that little sidebar on Versant and how we capture schema and some of the things we do. I went into that because I'm assuming most people are familiar with the create table, insert, update kind of model from the SQL language. The object-oriented model is a little bit different. Let's continue with some of the architecture. So, a little more common ground. Both these systems get used to build multi-tier applications. No surprise there. JDBC over TCP/IP, these buzzwords ought to be, or acronyms ought to be pretty familiar. On the Versant side, pretty much the same thing. Today, most people use JPA, Java Persistence Architecture, as the API. Again, that ends up being implemented on top of the TCP protocol. No surprises. Transactional access, yep. Asset-based, yep. Queries return data sets. Queries return collection objects. Pretty similar in concept. If you think of an object as a row in a database to a first-order approximation, that's a pretty good working model of an object database. So a lot of common ground between the client-server communication and the general interaction with the databases. Where some differences start to rear their heads is when we start looking at the transactional semantics. Both of these databases support ACID. Both of the implementations end up using log files to ensure things are consistent and durable. So again, more common ground. Probably the biggest difference that starts jumping out at you when you start looking at the transactional semantics and how we support ACID transactions is how we handle the concurrency and isolation problems. Versant uses kind of an older style locking model, object level locking, very granular, but still very detailed. Vectorwise makes use of multi-version concurrency control, giving you the challenge of version management, but also real easy snapshot isolation. Anyone know the term ACID, how far back that goes? I can't give you a t-shirt on this one, no, I'm not. But yeah, ACID, that term was coined nearly 30 years ago. 83. It's been around for a long time. I'm surprised by that. So when we look at this locking and isolation model, we see a big difference between these two databases. The multi-version concurrency control is really efficient. It's great for you don't have block weight graphs. The server doesn't have to do anything complicated. What ends up happening is a transaction ID marks every time a row set is updated within the database. So as multiple transactions are executed against the server, they have a snapshot in time, that is a given transaction point, that the data is looked at. And if data has changed, that's okay, your transaction can continue. It may have to roll back if you try to commit data to rows that have already been changed, but it gives you a very concurrent flow. And for a database that's designed for analytics, usually those operations are read-only, right? You're trying to extract value and information from static data. So multi-version concurrency control is the right approach for that kind of problem. Basically, I can still inject data into the system, do my background real-time kind of updates, and yet my queries can be isolated to a snapshot level. The drawback is updates always kind of go at the end of the database, and I have to do the extra accounting, and I have to make sure that at some point I may have to go through and clean out all those old versions to get back to the one unified view of the unit of the data to the database. So a little bit of overhead with that, but for read-only, and we think about the deployment model Vectorwise is using, it really makes a lot of sense. Versant is a little older of a product. I think earlier in the slides you mentioned Versant pretty much started back in 1988. So it uses a more traditional locking kind of format. If you think of how some relational databases use row locks or table locks, the analogous point within Versant is that object or row lock. So anytime I want to change objects and guarantee my synchronization, I can lock those objects and guarantee that no other transaction can come in and change it. And the locking model actually in Versant is quite complicated. There's all kinds of ways to enforce strict serialization or completely break the rules doing dirty reads. And again, that's going to depend on what you're trying to do. What sort of consistency and isolation does your problem actually require? The neat thing about Versant, when you do update objects, they typically go right into the same place that they were originally stored. So we don't see this database grow just due to continual updating. And that's actually really important for like that telecommunications company. example. When I change my service, it's pretty much my records that are being updated. There's no need to duplicate that kind of thing. So, with the storage models, or with with the locking and isolation problem addressed, let's take a look at how these databases persist the data actually physically on the disk and some of the differences. We see, again, some common ground and yet also some major differences. Both of them utilize multiple volumes. I think that's pretty much true of any modern database today. The ability to spread your data over different physical disk systems is very important for scalability. Typically, most of the customers are putting this stuff on top of RAID systems for reliability of the hardware. We come to a big difference, though, in I/O. Vectorwise is really designed to optimize that I/O process. The first block that they've done is set the block size fairly large, make sure those transfer rates are fairly efficient. In fact, with Vectorwise, you can configure that, so customers will turn that up, and that is a better representation for the type of data they're storing. So you can do that kind of optimization. Contrast that with Versant, we use a pretty small block. The reason we use a small block is if you look at the size of a typical object, they're not that big. They might be a few hundred bytes to a few K bytes. So being able to put multiple objects on a page makes it more space efficient when we start talking about swapping pages in and out of the server. So we see a big difference, however, with Vectorwise in that it stores data using a columnar approach. If you look at the literature, there's references at the back of the talk tonight. Vectorwise uses pretty much what you consider a PAX, which is partitioned across, attributes partitioned across the page, or decomposed storage model, DSM, which basically means one attribute per page. So by splitting things up that way, we can take advantage of the way the information is stored on the disk. We'll see what's done in just a minute. Contrast that with Versant, it's a lot more like a traditional database where the entire row or object is placed on a page, and it's the database's job to figure out what page to load in memory based on some sort of physical address, that is the volume it's on, the page offset, and the slot on a particular page. One of the differences, though, that Versant does support is its concept of clustering. You see that objects can be co-located on pages, which helps make it efficient to load things in and out of memory, as well as deal with multiple databases at the same time. So, a couple little differences. Let's look at them a little more. So, I hope this picture makes it a little more clear. With Vectorwise, with Vectorwise, we're putting the columns, we're organizing the data by columns. Basically, each one of those blocks, has one attribute in it. This lets us figure out what type of compression algorithm works best with that kind of data. It also lets us do things like add statistics to the blocks, so our query engine can be clever on what pages actually have to be loaded and looked at. Versant, on the other hand, is more like a traditional database, where the object is pretty much all the information for any given object is stored on one page. What we found through experimentation is the column base can really load data much more efficiently, much faster for scanning. The thing is, with the columnar database, it's quite often I don't need every attribute on a table. Quite often my reporting is only going to look at 2, 3, or some handful of attributes. With an object database, you almost always utilize the entire set of attributes with a given object. So again, we're looking at two very different architectural approaches and operational needs of these systems. And that's why you see these differences in file systems and storage differences. So, Vectorwise really relies on compression. We do this for a couple of reasons. First off, keeping things on disk compressed makes it a lot more efficient with your storage space. Secondly, when we load that information into the server memory, the server cache, We keep it compressed. We leave it in a compressed form because if you think about the type of manipulations you're going to do or scanning on that data, you really need to get that data into the chip, the CPU cache. So when we actually do get around to decompressing the data, it's because we're loading up the CPU caching structures for running the query engine process. This greatly removes a lot of the I/O bottlenecks in the system. And the min and max structures, the index structures that are set up with Vectorwise, every page essentially has a separate index put together. We can use that to easily eliminate pages that don't have to be scanned for the query process. This makes it really efficient to scan over the data, knowing you can skip certain blocks and not even have to load them into the processor for scanning quite Contrast that with Versant. Again, that page is likely to contain a complete representation of one or more objects, and the whole storage engine on Versant is really designed to get an object and deliver it to the application. It gets an object by this thing we call logical object ID, or object ID for short. This ID is kind of like a social security number in the States, or in database terms, you can think of it as a universal primary key. It's one number that defines the identity of the object, and the database's sole or main job is to deliver that object when asked for it. It also, the storage engine deals with the variabilities that you see in object languages where object sizes vary. You have collection classes of variable lengths. So you have that kind of thing built into the object page swapping system for Versant. But fundamentally, all the objects that live on the page get pulled in and out of memory as the application requests them by the object ID. That page boundary, as I said, is pretty small, especially compared to Vectorwise. But the reason is, most of the time your objects are pretty small. I can co-locate a lot of 2K objects on a 16K page, and I'm going to have very efficient loading in and out of those objects. The other thing about that object ID is it's used to represent pointers. If you think about graphs in memory, those graphs are connected by pointers and references, and if you're a Java guy, Versant has to manage and implement through some mechanism those graphs. And we do that with this object ID. So if you think of it, the pointer in memory is the object ID in the database. My little example here, I've got my red object that's in memory. It's got pointers off to two other objects. If the application needs them, they're going to follow that pointer, see that it's got no address, it hasn't been loaded, go back to the server and say, hey, hand me the object 0.47, and the server's going to look that up and deliver it back to the client. And loading that page into server memory and constituting the object, serializing it over to your application. So that's what's going on the server side. We accomplish that. There's nothing more optimized in an object database than that lookup of the ID to physical location of where it resides in the disk. The goal is basically to do that in constant time. The other thing about the storage system with Versant is you have the ability that those pointers can traverse databases. Not only do they recognize or identify a given object, if that object lives in a different database, we can pick that up, and the application can pull stuff in and out of multiple databases. So Versant actually lets you cluster your data across different systems. So, talk about the storage system, a little bit about Vectorwise's compression strategies and its automatic indexing with the min-max ID, the min-max statistics on the page. These are databases, so let's talk a little bit about how they get queried. Yes?
I'm not sure I heard, how do you do observability in the database? Like I heard that you were able to efficiently...
Yeah, I probably didn't emphasize it. The durability is in part handled by the logging files. So in both cases, Versant and Vectorwise will update the changes in the server memory, but prior to that, those transactional changes are written to disk. So later on, if the server goes down, you have those transactions stored on disk, And as the database comes up, they can replay it and reintegrate it into Versant, the data volumes, or in Vectorwise in particular, data pages. So it's pretty much the same between both products. It's a logging strategy that's coupled to the transaction semantics. Okay, good question. So, queries. Vectorwise, you might guess, SQL, no surprise, SQL database. Versant, it's going to be JQL, and I'll go through one quick example of that. Indexes. Versant really supports a bunch of indexes, which I find kind of interesting because the whole point to an object database isn't so much to query, it's really to make use of the pointers and navigation. You think about the graphs that are typical problems that Versant gets applied to, it's following the pointers. But you have to start somewhere, and the typical pattern is do a query, get an object, work from the graph that that object is connected to. On the Vectorwise side, it's a little different. We're typically analyzing reports, trying to find common patterns, doing aggregations and large chunks of data. So in fact, one of the goals of Vectorwise is so you don't even have to tune it. But if you want, you can add an index on any one column of a table. And then that table itself is always maintained in sorted order. Versant is very different. I can add an index on any attribute I want. The indexes are stored completely different, separate from the table, and they get used by the query engine as needed to support the efficient lookup of whatever particular object is bound to that key. So we have an intricate indexing system on one side and a very automatic indexing system. In fact, most of the time when our application engineers in Vectorwise, they recommend start with not even adding any indexes. The automatic indexes are part of the system. And the way we operate on the data in memory and with the CPU cache actually make it fast enough that you don't need to do a lot of special indexing to make the queries efficient. In fact, let's look at that problem. A little bit of history about Vectorwise, where it comes from. So this goes back to about 2003 from a research group in the Netherlands. They started looking at different performance benchmarks and said, gee, I can write a custom C program to address this particular benchmark and get about 100 times the performance out of on the benchmark versus having to do it through a relational database. Just picked a couple of relational databases there that was being typical. So why is that C program so much more efficient for grinding on the data and hitting the benchmark? What's going on? Where's that 100x performance coming from? Well, that actually spawned a research problem, or a research group in the Netherlands, referred to it as the X100 project. And what they did is they looked at each of the steps. We've already talked about a couple of them with the storage compression, the page indexing, and the columnar store. But they also looked at the execution, what type of processing is done. Looked at the way the compiler optimizes code when you compile it. We've had 35, 40 years of compiler technology that often isn't utilized on databases because they're too scattered in the way they have to jump around and process your data. But when you start organizing it by column, you start dropping it into the CPU cache. You start writing your instruction, your query operators in such a way that they don't have branches, and you can grind through this data in a very efficient manner, taking advantage of vector operations inside the CPU instruction set. That's when you start getting the efficiency that's inherent on a micro-tuned C application that we have in the benchmark slide. So when you put all these things together, they didn't quite get the 200 or the 100x performance, but they came pretty close. So going back to that original C program and the benchmark, which was 0.2 seconds compared to 25 or 26 or 28 seconds, when they wrapped all the database mechanics around it, it was still under a second, 0.6 seconds with the equivalent benchmark compared to the C program. That's actually not bad when you think about all the things a database has to do for you. Transaction semantics, the journaling and logging that happens, those kind of things. So that was the focus of the Vectorwise query engine. So basically to recapture those performance features and then couple that with a SQL database. How many have heard of Ingress before? Yeah, Ingress has been around forever. Well, Vectorwise uses Ingress at the upper levels. So what we have here is the normal Ingress database system. It's typical row storage. Where in the slides that you have with Ingress, that's still there with Vectorwise. You can actually use those kind of tables. What Vectorwise drops in is this X100 project, Columnar storage, the rewriting of the query operators to take advantage of the CPU architectures more efficiently, and redesign the operation, and then rewrite the query to be more efficient in the execution. So that's kind of how Vectorwise fits within the Ingress architecture. We still rely on Ingress for all the upper levels of the SQL parsing and all the tooling and installation stuff. But at the core is a very different query engine that breaks the problem down. So when you put all that together on the query side for Vectorwise, you really see a bunch of clever ideas that have been floating around the computing space for a long time, really strung together to make for a very efficient, high-performing analytics database. So we start with the vector processing, keeping the data in the CPU cache, limiting the amount of I/O through strategies like the compressed column store and the operational storage indexes with min and max values to exclude predicates. Finally, breaking that problem up into multiple cores to take full advantage of the number of CPUs and cores on the target system. So let me bring this back to that first slide. I apologize for the marketing slide there where we have the performance and the dollar cost for the machine. This is how we can get those benchmarks on really cost-effective hardware. All right, a couple more slides here, just about done. So all that's done with a SQL query on the Vectorwise side. Versant, not so much, not a SQL database, definitely the NoSQL camp. But you still need a query API to get at that first object from which you can navigate. So the way query works in Versant is there's some sort of object query language. And for this example, I'm just going to use JPQL. That's the JPA, Java Persistence Architecture query language. Industry standard. JSR 220 is the Sun Community Group. If you want to look at that. It is predominantly a relational database standard. It deals with a lot of complexity with object relational mapping. None of which that you have to deal with when you use Versant. Pretty much with Versant, you just define your classes, mark them as entities, tag the ID, and now those classes can go into the database. So hope this isn't too much Java, but what I have here is two classes. I have a book and a person, and my book class has one real simple collection on it, and that is the authors of the book. My query, again, is also really simple. I want to go find all the books in the database that have given author. In this case, Smith is the last name. So that's how you formulate the query. Notice using the string format looks a little bit like SQL. A little bit. I identify what I want to select from what target table. In this case, we call it a class in object databases, but you can think of it as a table, it's a first approximation. And then inside that book, I know I want to look at the authors. So you can see my meta variable here, the reference to look at the author class, and I want to know some particular value inside of that collection. So this, I'm going down one set of collection. This is actually a pretty simple query. Quite often with Versant, we'll see really complicated multi-level depths of collections being traversed. Now what the server is going to do is going to take this string, compile it, figure out that it needs to look at the book class, and start scanning the books, find all the books in the system, and then it's going to look at the authors. And it does that by following pointers in the author collection. So even on the server, those pointers matter, and that's where Versant gets its efficiency from. In a typical relational or mapping type approach, often those things are going to become joins. Those joins, the server is going to have to do the first join to figure out what books and authors all line up and go through that. With Versant, because it understands the storage, the pointers at a storage level, it literally just kind of hops around in memory, going to object and object to evaluate the predicate clauses. Finally, when you execute that against the server, what do you get back? You get back a list of objects that your Java program might work on. In this case, my result set is just going to be a list of books. What you do after that, I don't know how you write each code. So it's a very different kind of query model. Query, bring it into the application, memory, and work with it from there. Just a couple more points about these links or voids. For the storage to be efficient on the Versant side, it has to be able to deal with these pointer relationships. I mentioned if you're using OR mapping tools, typically they can handle the join operations in the SQL space. Versant doesn't do that. We avoid those. In fact, in all our processing on the server side, we don't even have a join instruction. And if you think about it, often these relationships, they're fixed. You know, if you look at the example here, blog to blog entry, book to author, friend, you to your friend, those things don't change that often. So why recompute them with a join every time you want to merge the data to formulate the information you want to send back to the application? So the storage engine in Versant inherently understands these pointers and can follow them and evaluate the queries to efficiently make up for its, say, older style of storage, especially when you compare it to Vectorwise Columnar storage. So by using these pointers, keeping track of them, not pre-computing them, being able to directly traverse them on the server side as well as on the application side, the query engine becomes very efficient in being able to return that initial top-level object. And then, like I said, your application has a top level, it goes from there. So, let me just give you a couple of finishing thoughts. And between these two architectures, we saw a lot of common ground, similar data models, common concepts and transactions, and master behavior, similar logging schemes, different at indexing, file storage, and real detailed bit level manipulations of the CPU cache and things like that. But they're two systems that are targeted at very, very different problem spaces. And that's why it's important to think about the problem. You know, are you looking at something like the 3,000 classes and 4,500 interconnections between these classes? Or are you looking at getting fast real-time reporting, from a wide range of reports in a business intelligence system? I've been working with databases and database systems for about 15 years now, and I definitely, this last name, one size does not fit all. It's a big marketplace, as we saw from the 451 slide, but there's a reason why these different products exist and how they solve different real-world problems. So with that, Eric, and I thank you for your patience.
Derek Laufenberg, Director of Systems Engineering for Actian. Thank you very much, Derek. Let's go on with questions from the audience. Yes?
Who does the garbage collection on the database? So are you responsible for putting up the objects and the fish using them? So
On which database?
on the object.
On the object database. That's a good question because the storage model and implementation model so closely follows the memory model. You really do have what's called persistence garbage collection as a problem to think about within the application. Typically what gets done is the object model gets designed and they exploit a feature called cascading deletes. So if I delete an object, just like we had the persistence by reachability, cascading deletes kind of work like that, only opposite. When I delete my top level object, I can identify the other elements that are connected to it. Basically, the parent object takes care of its children. So when I delete the parent object, it'll go through, and in C++, you'll implement this with destructors, or with JPA, you can implement it through the cascading deletes in the class. The programmer identifies that, and once they identify that, the database will take care of it. But it is really directed at the application level. So you can kind of break that model if you say deleted an object without using your application code, then that cascading effect wouldn't happen.
Yes.
So most NoSQL databases have like key value pair kind of storage. How does Versant?
I kind of think of an object database as a superset of both a document database and a graph database and a key value store. You notice the indexing capability of Versant, you see V trees and hashes. It's really easy to build a key value store with that. I mean, an object database really at the heart, that's why I kind of spent a couple slides on the object ID. That really is the key. Where it's a little bit different is I can give you that one number and you can get the object regardless of the class. So that's a little bit challenging sometimes with other key value stores. You often get a blob that you have no knowledge. You have to very carefully craft your code. With Versant, I can give you the number, it's going to know the class, and it's going to instantiate the object of that particular type right in the JVM. And by the time the machinery hands it back to your application, it's fully formed as a Java object. You just plain old Java from there.
Yeah, so I'm trying to understand object databases a little bit. I come from a sort of a relational world.
Most people do. I get that a lot.
And in the relational world, you often have to access the data outside of traditional programming languages. So SQL is a good language for that, and you have different APIs to do that standard. And also, you sometimes have to do analytics because it's of the relational thing. I'm wondering, with an object database, how do you extract data and do some analytics? So you don't really do a whole lot with an object.
That usually, you look at the use cases of something like Versant or any object database. Before Versant, I worked with Poet or Fast Objects, which is another object database technology owned by Actian. That tends to be a very highly engineered application with that domain model built around it. And that's really the primary mechanism for interacting with the database. So you end up building constraints into the application code. And quite often when you build an application, one team might do the persistence architecture, put together a set of class libraries for the rest of the team to use. So the database expertise kind of ends up in one group. Really, it's designed, that data model has got so many constraints. It's a rich domain model. It's not an anemic set of DTOs or something. So you really use it with that set of Java classes that are behind it. So that's where things like constraints get implemented.
I'm sorry. Like if I wanted to write non-Java or C++ shell scripts or something to access the data, like you can do that with relational.
There actually are ways to do that. We have generic interfaces for Java. There's a Python binding you can use to kind of go in and extract an object. And there are object-oriented reporting systems like BERT that can be used on top of it. Typically, though, Versant gets used in this operational context. So quite often, they'll either design a handful of small reports that might get implemented in Java and execute against the system, or they'll set up transfer ETL rules, basically to take the data out of Versant, apply some sort of processing to it, and dump it into a reporting database like Vectorwise or a more conventional SQL database, where you really do have that standard SQL language, which is a huge advantage for reporting and connecting with BI tools. I will say most object databases, Versant included, one of the weaknesses is kind of that ad hoc reporting. It's really designed now for rich, complicated domain models, and that's not really where you want to do your reporting. You might rely on that model a little bit, but you don't want to have those reports running while your database is really serving the business. So it's a trade-off.
Could you talk about what kind of platform do those two databases run?
Yeah.
And how about horizontal scalability?
Okay.
How many nodes?
Yeah, good question. So both are designed to work off of commodity hardware, standard operating systems. Vectorwise uses uses Linux and Windows. Versant runs on Linux, Windows, and Solaris. Most of our deployments now, I think, of both products put the server on Linux, probably running 2.1 into Windows. We don't see as much server Solaris use these days. 64-bit or 32-bit architecture. Again, you don't see much of the 32-bit architecture anymore. In fact, I think Vectorwise is only 64-bit. Versant, I still have some customers using 32-bit.
On top of that, and then how many nodes will be added?
Oh, right, the horizontal versus vertical. Well, Vectorwise is actually designed to be a scale-up vertical database. Because of the tricks we play with compression, paging, and all that, it really is a single node. You'll see that even in our literature. There's another product in the Actian portfolio that is a SQL database that is designed to spread things out, and it's called ParAccel SMPdb. But so Vectorwise is really a single node scale up. Versant can be either. We'll certainly take advantage of that scaling up. I mean, I don't know any database that doesn't benefit from a large chunk of RAM on the server. Versant's no different. But with the cross-database links that is fundamental to the storage engine inside of Versant, you can have multiple databases within the connected set. Versant does a two-phase commit across any databases that are part of it. You can actually even use, Versant supports XA architecture, so you can do two-phase commits across, Versant as an object database, couple that with a shared transaction space against a relational database, XA.
So I wanted to ask how you're sort of handling dynamic schemas.
Yeah, schema change kind of hits you in the face with an object database because programmers love to change code, right? And every time you change code, that's effectively your schema. So an object database has to address that problem up front. The way we handle that, aside from the mechanics of flags and stuff to control and the configuration, whether you're allowed to do schema changes or not, but it's when we extract that schema information from the header or from the bytecode, that becomes a version. We understand that objects are stored with this particular version. And if the version gets updated, the objects get left in that old format, but the server actually knows about both versions. So the application really only has one version, the version it's compiled with. So the server takes care of basically unifying that on the object schema marshal. So if you add a record or add an attribute or delete a record attribute from the class, that gets addressed at the time of marshaling. And of course, when you commit that object back, it's going to be updated and stored in that new version. So, also the object lifecycle mechanics in JPA or other bindings also have a mechanism for dealing with, hey, this object is a newer format. Do you want to trap something in the code and do a fix-up on that new attribute you added? So there's easy ways that the developer can catch those cut points and make sure that the version of the schema and the object match the application's intent.
So I have a follow-up question. Sure. So does Actian have like a product in its lineup? It is for dynamic schema where you want to have the richness of a person, class, and everything in it, but store different attributes.
Yes. Actually, I see that all the time done with Versant. Because you've got these collection classes, well, what if my collection actually just contains a key and a value or a key type value tuple? So you can have essentially a fixed schema that is extracted directly from the class. And one of the entries in that class could be a collection of generic tuple types. And I've seen customers build those kind of meta models where you have that really highly dynamic data type. In fact, what I've seen them do then is say, every class we created had this dynamic type. Why don't we move that dynamic type into the static compiled attribute of the class and then catch it and fix it up as part of the object lifecycle loading? So it's pretty easy to handle those dynamic classes within the Java or C++ model and even query into them. And then later on decide, no, I want that to be a fixed part of my class. That's all the transcode is. So,
Next question.
Can you compare it to object store, the original object store database?
The original object store. Probably can't. It's been way too long for me since I've worked with the object store guys. And, so, sorry.
Just one more question. That's right.
You mentioned Verb. Do they both work with Verb?
I don't know. That's a good question. I imagine you could probably get Vectorwise to work with it since there's a JDBC adapter. But when I think of Bird, I tend to think of this, pretty object to reporting. I'm working directly with my class model. And typically, with Vectorwise, you're working with it at a higher level of abstraction, through some of the BI tools and partners that Actian works with. So, that's a good question.
Okay, Derek will be here for one-on-one questions, so anyone who didn't get a chance, feel free to come up now and ask him directly. Thank you very much, Derek Laufenberg.
Thank you.